Hi, good afternoon. I am Naeem, and I and Naguib will discuss our part of engineering mathematics, as professor has given us the task to give some preliminary lecture on this engineering mathematics. So there are different topics in engineering mathematics. The one is differential equations, integral, electric circuits, geometrical mathematics, and there are also some other topics which are very basics and already covered in our course. So we will not talk much about those topics, but mainly I will talk about the differential equations, and Naguib will cover up the rest of the things in the presentation. So now I will go to the differential equation part. So what is a differential equation? Differential equation is basically a mathematical equation for unknown function, in which the unknown function lie within that differential equations. Like if I have a differential equation y dash, and I have to find the unknown y. So this y is inside this differential equation. Now, there are a lot of usage in engineering, physics, economics, and other disciplines of these differential equations. Like I will give you a simple example. Like suppose a ball is falling from the rooftop, right? So if we want to find the acceleration of that ball, right? So there are actually two things acting on that ball. One is the acceleration due to gravity, which is pulling the ball toward the earth, and the second one is the resistance of the air. So the resistance of the air decelerate the ball. So we have to like model the velocity of the ball in terms of the resistance of the air, and then when we take the derivative of the velocity, we get the acceleration. So to find the net acceleration, we take the differential between the acceleration due to gravity and that acceleration which we got from the derivative of the velocity of the ball. So now, what is the nomenclature of the differential equations? Basically, there are two types of differential equations. One is ordinary differential equation, and the second one is the partial differential equation. So what are ordinary differential equations? Ordinary differential equation are basically an unknown function of single variable. Like suppose there is only one variable y, so it contains only one variable unknown function, and it may have it may be of 1 degree or 2 degree or any degree. It depends on the number of derivative, right? Like if we take one derivative, it will be of degree 1. If we take the double derivative, it is of degree 2, like this way. And what are the partial differential equation? Partial differential equations are basically based on more than one variable. So we have to take the partial derivative of those variables. So it is a little bit complex than the ordinary differential equations. And there are some equations which are of mixed type. So there are basically three types of differential equation. One is ordinary differential equation. The second one is the partial differential equation, and the third one is the mixed type. Now, differential equation may be linear or non-linear. When the power of the unknown function or the derivative of the unknown function is 1, then we call it linear. Otherwise, we call it non-linear differential equations. Now, there are different methods to solve the differential equation. We have to calculate the unknown function from those differential equations. So there are different methods. The first one is the Euler-Cauchy method, which is a numeric method, and it is iterative method. Like we will take steps to go to our final solution. Like we have here h is the step size, right? So we will calculate y1 from h0, then y2 from h1, and in this way, when we converge to the solution, we will stop there. That is our solution, and this is called the Euler method or numeric method. Then there is a second method called direction field method. Here we do plotting of the slope. We don't solve the equations. We just plot the slope of our equation, and then at specific point we find the slope there, and that slope give us the solution of the unknown function. Then there is a third method to solve the ordinary differential equation, which is separable ordinary differential equation modeling. So here what we do, we separate the x terms and the y terms on each side. So then we solve it by using the integration method, like what we do in normal integration method. Then there is extended method, in which we reduce the equation in term of y over x. Like those equations which we cannot make it separable easily, we adopt this method. Like we make the form of y over x, and then we solve it using like y is equal to ux and y dash is equal to u dash x plus u. Then there are two form of equations, like whether it is exact or not. So we have to check the exactness of that equation. So there are like different methods how to check the exactness of that equation. So if it is not exact, we use the integrating factor to make it exact and then solve it. And there is also another way of solving those ordinary differential equation. Like if I have second order equation, so what I do, I reduce it to first order differential equation and then solve it using the integration method or any method which I discussed above. There are also homogeneous and non-homogeneous differential operator. Like I can solve it by using the differential operator methods. These are very easy methods to solve. If it is homogeneous, it is very easy. If it is non-homogeneous, then we have to find the particular solution as well. So and now the last one is the Laplace transform method. Laplace transform method is a very easy way to solve the differential equation. We don't have to go to the particular equation, or we don't have to find the general solution. We can easily find the initial condition solution by using the Laplace transform, and we don't have to find the particular solution as we have to do in the other methods. Now, what are the application of the differential equation? Actually, there are a lot of application of the differential equation, but I will cover like 2 or 3 application of this. Like one is the radioactive decay. So like if I have some radioactive elements, so with the passage of time it radiates energy, and it will decrease, so we have to find the half-life of that element, and then from the half-life we can know about what is the for how long this thing reduced to this much. So there is one application of this. So what we do, we model our statement into a mathematical model. And like what is radioactive decay? It is like the change in the quantity of those things. So we explain this change as a derivative, right? So we convert it into a mathematical model, then we solve it, and when we solve it we get a general solution, and when we put our values in that in this equation, we get the solution of our problem. Then there is another basic application of this, like suppose in our university building, we turn on or turn off the heating or cooling of our building. So like when we turn off the cooling of the building, so with the it depends on the external environment, right? So it will get warm with respect to the outside environment. So we will model this in our differential equation form, then we solve it, and then we from this solution we can know that what will be the inside temperature of the building at each and every interval of time. So this is the second application of the differential equations. Now, I have solved like one basic problem on gradient descent method using the engineering mathematics approach. So, like, what is gradient descent? Gradient descent method is like the way of optimizing our problem, right? So, there are basically two types of gradient descent. One is stochastic gradient descent, and the second one is the simple gradient descent. Gradient descent is basically we iterate through all of our samples and then we update our weights. And what is stochastic? Stochastic is a little bit time computationally, it is a little bit less expensive than the gradient descent method. In stochastic gradient descent, we we go through some samples and then update the weights. We don't have to go through all the samples and then update the weights. So I have implemented stochastic gradient descent method on a very simple equation like this one, which I also discussed in the midterm proposal, and I got this solution. Now I will call Naguib to cover up the later things, later presentation part. Thank you.
Thank you, Naeem, and thank you, everyone. So I will cover the remaining parts of the preliminary study about the engineering mathematics. We have covered this topic not only by the textbook of the professor he referenced to us, but also by the examples that we posted in our Q&A sections. I will talk about an example given by Pio. This is a differential equation as well. He solved this differential equation very quickly, and the solution can be shown in this way. It's a very simple first order differential equation. Also, I'm given an example of a gradient descent, much like the example of Naeem. So he was interested to compute the deepest increasing direction or deepest decreasing direction, which what we call in the gradient descent or gradient ascent directions. So let's say that we have this kind of surface in 3D, and we are interested to find the gradient descent or ascent at a particular point. So by definition, gradient means that we need to know the differential components of this function in both x and y and z. So this is kind of a partial differential equation. We can compute it, and then we can substitute the point we want to compute the gradient at. From here, we can normalize the vector, and this is the gradient descent, and the minus of this is going to be the gradient ascent, or otherwise the opposite. So this is for differential equations. It's a very important part of mathematics and physics, and it's play a lot, like an important role in our life, as well as the integral as well. Integral is basically the exact opposite of a differential operator. However, in integral operator, we have some uncertainty about the bias or a constant that come out, and the only way we can actually find the exact solution is to define a boundary. And so when we are trying to integrate in mathematics, luckily we have so many boundaries. These are basically constraints in which the integral is operating in, and this help us find the exact solution for this particular application. For instance, if we are trying to find the surface of an area, we define this area itself, and this become a surface integral, and we can find the area contained within this boundary. Volumetric as well is called volumetric integrals. And if this trajectory or this path we are integrating over is closed, we call this closed path integrals. So I will give an example from actually Lakov gave an example in Q&A, and I will explain it at here. He was interested on finding the surface integral of y over a cylinder in XYZ space, in 3D space, defined by this equation, in which K here defined the radius of this cylinder. This is a vertical cylinder in Z. And his boundaries, which is very important, is Z equal A and Z equal B. So he want to find the integral of y over the surface of this cylinder from the height of A to the height of B. One thing we will notice a lot is that when we do integrals over a surface that have circles, it's always easier to use a polar or a cylindrical coordinate system instead of a Cartesian coordinate system. So this is exactly what Lakov has done. He converted the coordinate system from XYZ to R, theta, and Z, which is the cylindrical coordinate system. In that sense, y is defined by k sine theta, and we want to integrate k sine theta with respect to the area. But before we do that, we need to know what is the step of the area. So what Lakava did is find the cross product of r theta and rz, the derivative components of r in theta and z. Once you do this cross product, you will get a surface normal, what we call surface normal, and the magnitude of this will give you the unit area. So the magnitude here turned out to be k. So when we derivate y, we actually substitute y by the component k sine theta, and the derivative of the area is actually magnitude by k, and the derivative of an area in the cylindrical coordinate is basically dz d theta. Since we are interested in bounding the integrals from a to b, the z is bounded by a and b, and theta is not bounded, so it goes all the way from 0 to 2 pi. This is what we call a closed loop. And he computed the integrals, and they turned out to be 0, and he gave the example on iCompass as well, on Sagi, I mean. In the textbook, we saw so many examples for circuits, and the circuits is such a good example to explain the mathematics, in particular for differential equations, and I will come to it, but first I will explain the basics of a circuit. A circuit, it contains from electrical components that can come as like resistor, capacitor, or inductor, and a voltage source, usually donated by voltage source like here, or sometimes it's a current source, but in this example it's a voltage source. So the voltage source will actually power us a current through the network, and we are interested to know what is the current in each part of this network. So first thing we can do is apply something called Kirchhoff law. That means that it's kind of an energy preservation law. So at each point, the currents that are coming in are equal to the currents that are coming out. We can donate I1 at here as x, and I2 as y, and I3 as z. So we can know that I1 equal to our x equal to y and z. So x minus y minus z equal to 0. This defines one equation. We need 3 equations to find these 3 unknowns. The other 2 equations can be defined by the voltage drops. So we know the voltage source here is 90 volt. Because of this current going through the resistor, this will create what we call voltage drop, which is V1. And also the current going through this resistor will create a voltage drop that we call V2. And we know that this point and this point are connected, so they have the same voltage. So this closed loop define kind of a voltage equation. We can define it by saying that 90, which is this voltage, minus x multiplied by the resistor. This will create a new voltage drop at here. This is minus 10x. And then minus 30. 30 is the resistor multiplied by the current, which is y, equals 0, because this is eventually the same node. And finally, we know that because this point is connected and this point is connected, this is what we call parallel configuration. The voltage at here is equal to the voltage at here, which means y multiplied by the 30 equal z multiplied by 60. And we can solve these 3 equations on the 3 unknowns, as shown in this our example, and these are the results. Similarly, there is another example at here. We can form it using the same methodology. Interestingly, in the textbook, the solution here was not really correct, so we had to come up with this solution quickly by ourselves. However, in circuits, the components are not necessarily resistors. Sometimes it's a capacitor or an inductor, and they have a unique behavior. If we thought about an electric circuit as a water flowing through the river, in that case, a resistor is like a rock that is resisting the water flow, and the voltage is basically the pressure of the water at each point. In that term, in that kind of notation or example, the capacitor will be something like a tank, so a tank of water. So the river is flowing like a lake or something. The river is flowing through the lake. And an inductor is like the waterfall. So when the river hits a waterfall, it accelerates really, really much. The difference is a resistor does not affect the rate of change of the current. However, an inductor actually accelerated and a capacitor decelerated, and this is translated into the equation in this form. Here's a small issue in the terminology of the book as well. This is 600, but this is integral of I. So basically the inductor will have a differential component, the capacitor will have an integral component of I, and the resistor is just a unique operator of I. in these examples, we are interested on simplifying it, because instead of using a differential component and an integral component in one equation, we want to have a fully differential component or differential equation. So we denote I as dq by dt. Q here represents the charge. So what it means is physically the amount of electrons that flux through the network, this is what we denote as Q. And the I, which is the current, is the rate of change of this flux of charges or electrons. So in that sense, this equation can be a second order differential equation, and we can solve this equation by integrals. However, when we integrate, we have to be careful about trivial solutions. So we have actually two solutions for this example. One is the direct solution from the integral, which is QH at here, but one is a trivial solution. Trivial solution means that what if Q equal, the rate of Q equals 0, means Q is a constant. So we can say that if Q is a constant, then that constant is basically, this is going to be 0 and this is going to be 0. So that constant is basically 3/50. And that denotes the trivial solution to that equation. And the total solution is basically the two solutions added together. And we can notice directly that we have still the two constants we need to find out about. And as I said, we need to use a boundary. And luckily in this example, we know the boundary. We know that at the very beginning of this circuit, there is no current. It was just connected, so the current is 0. So at a time equals 0, the current is 0, and the number of charges going through the network is also 0. Using these two boundaries, we can find the C1 and C2 using these two equations. And then once we've done that, we can differentiate Q by T and get an I, and this is the total I of the network. So this is a solution of how to find the current through this network. You'll notice that solving this equation and finding the current is a little bit complicated for a very simple circuit like this. That is because we are trying to use differential equations and integrals. However, commonly we use either frequency domain or Laplace transform to find the ordinary differential equation solution, just like what Naim said in the solutions for differential equations. So here's another example. And the solution for this example, rather than trying to find solve this differential equation for Q, we can directly take the Laplace transform, in which it will be S squared Q plus SQ. You know, the one derivative component is equal to S. S is the Laplace operator. And then we can find the inverse Laplace of this formula, and this will give us directly the Q of T, which is very, very simple and very easy to do. And then if we need to, for example, find the voltage at here, the voltage over a capacitor is Q over C. So we can divide Q over C and get the voltage at here. This is also provided by the code in R. Finally, there was an example given by Sudip of some geometrical problem in which he is interested to find the representation of an inequality formula. You want to know where is the region in space that is below 5x equal 1. So 5x equal 1 represents a linear or a line. And if we need to know the area under it, he provided some solution and he plotted even in Sage. So that concludes our presentation. Thank you very much for listening. And if you have any questions in the future regarding mathematical engineering, you can feel free to ask me or Naim at any time. Thank you.